The first you need to understand in probability theory is the sample space, events, and, well, probability itself. Once you understand the relationship, the foundation of your career in stochastic is set. The sample space, sometimes also called the outcome space, is, as the name implies, a set containing all possible outcomes of a random experiment. Whether an outcome is seen as likely or unlikely doesn't matter. Everything that can possibly happen must be included in this set. This set is typically represented by a capital letter omega. The elements of this set, the outcomes, are labeled as lowercase letters omega. A sample space can have a finite number of elements, like in the random experiment rolling a die, where there are exactly 6 possible outcomes, represented by the numbers of the faces. The elements can be counted and labeled. However, the sample space can also be countably infinite, like in the experiment of randomly picking an integer, where omega is the set of integers, or it could be uncountably infinite, such as the interval representing the daily return of a stock, which might drop by up to $500 because that's the amount I've invested, or rise to infinity. In this interval, there are infinitely many possible outcomes, which makes it impossible to simply count them. In short, the sample space is defined by the corresponding random experiment. Okay, let's take a closer look at the dice example. I get it, dice examples seem lame, but they are damn useful for understanding basic probability concepts. So the sample space in the dice example is this, representing all possible outcomes. Pretty straightforward, yes. Here, all 6 outcomes are equally likely. In this case, the underlying random experiment is called a Laplace experiment. But here's the thing. Probability statements aren't always about single outcomes. You might want to know the likelihood of rolling only even numbers or odd numbers, or numbers greater than or equal to 5, or something similar. These sets, made up of several outcomes, are called events. Specifically, if an event contains only a single outcome, it's called an elementary event, or also atomic event or sample point. The empty set is also considered an event, referred to as the impossible event, because it can never occur. Omega itself is also an event, known as the certain event, because there is 100% chance you'll roll one of the 6 numbers. So an event is simply a subset of the sample space. And yes, that includes the empty set, because it is a subset of any set. However, it's often not mentioned explicitly. Events are usually denoted by capital letters, or with an index as I'm doing here. In the dice example, there are 64 possible events, meaning subsets of the sample space. For finite sets like this, the calculation is straightforward. You just calculate 2 to the power of the number of elements in the set, also called cardinality, has 6 elements. So we get 2 to the power of 6, which equals 64. An event occurs when the outcome is part of the event, meaning omega is in A. So the event rolling an even number happens if you roll a 2, 4, or a 6, which are all elements of the sample space. The cool thing is, since events are sets, they can be combined according to the usual rules of the set theory. We can say, for instance, A union B occurs if A or B occur, or both. A intersects B occurs if both A and B occur. The complement of A occurs if A does not occur. A quick note. In a random experiment, only one specific outcome can occur, like rolling a 2, but that outcome can belong to multiple events. This means that several events can occur at the same time. Now, usually certain events are more likely than others. So to represent this probability, we introduce the function p. P stands, as you might guess, for probability. By this function, an event is assigned to a value between 0 and 1. To call itself probability, this function must satisfy a few important but intuitive axioms. Normalization. P of omega equals 1, which means the probability is 100% that one of the possible outcomes will happen. Additivity. If A and B are disjoint events, meaning their intersection is empty and they can't happen at the same time, then the probability of A or B occurring is equal to the sum of the probabilities of A and B. From these axioms, you can derive other intuitive and useful probability rules. Since our dice example is a Laplace experiment, meaning each outcome is assumed to be equally likely, we can define the probability as P of A equals absolute value of A divided by the absolute value of omega. That is, the number of outcomes in A divided by the total number of possible outcomes. For example, the probability of rolling an odd number is calculated as follows. Since there are 3 odd numbers out of 6 possible outcomes. So the probability is 0.5, meaning there is a 50% chance. You can easily see that this definition satisfies the axioms of probability we discussed. P only maps to values between 0 and 1. P of omega is equal to 1, and the probability of 2 disjoint events like this is the sum of their respective probabilities. However, these axioms apply to non-Laplace experiments as well. Also, calculating probabilities might be more challenging, since individual outcomes could have different probabilities. That is, as you will see, where the cool distribution functions come into play.